Okay. So today we're going to be doing Introduction to Pulmonary Physiology and Lung Volumes. Very easy. There's only like 3 or 4 concepts that need to be explained, and the rest is all just memorizing. You can expect like 3 to 4 questions from this lecture in your final. So I'd suggest that you do it well. And then inshallah, if we just pay attention in this lecture and go over it before the final, everything should be good. So I don't want to waste any time. Oh wait, let me introduce myself. My name is Immad. I'm a second-year medical student. And if you have any questions throughout the lecture, you can ask me anytime. Don't worry. Put it in the chat, and we'll also give you opportunities to unmute and ask questions at checkpoints. If you want to ask me something later, you have my number and my email ID. You can also ask me stuff over there. Okay, خلاص. Let's start now. Okay. So before we start, learn some symbols, and these symbols are going to help you know or understand what we're talking about. If you don't understand these symbols, you won't understand what we're talking about. So let's go over them. Compliance is represented by capital C. Concentration of gas in blood is capital C. And I know they're both capital C's, but you would know the difference depending on the context. If they're talking about blood or something related to the circulatory system, it would be concentration of gas in blood. And if we were talking about something related to the lungs or the chest wall or something like that, then it would be compliance. You have fractional concentration, that's capital F. And fractional concentration is just the percentage of something out of a whole. So like a fraction of a gas in the blood would be fractional concentration, or a fraction of a gas in the air that we inspire or take in. Then we have pressure and partial pressure. They're both denoted by a capital P. We have blood volume, which is denoted by a capital Q. And then we have blood volume per unit time. And per unit time means per second, per minute, per hour, and it depends. It will be given, if it's ever given to you, they'll mention the unit of time. It's represented by a Q with a dot on top. So Q dot is a blood volume per unit time. You have respiratory exchange ratio, which is R. You have gas volume, which is a capital V. And you have gas volume per unit time, which is V with a dot on top of it. And you'll start to notice a pattern here that whenever you're talking about per unit time or you're using time as a unit, you'd see a dot on top of the symbol. And then saturation of hemoglobin with oxygen is S. Now, this may seem a little foreign, but once we go over the lecture, you'll see that it'll be natural to you, inshallah. And not all of these are super important, I'd say. For this lecture, just know this one, concentration of gas in blood, fractional concentration, pressure, blood volume per unit time, gas volume, and gas volume per unit time. The rest, you will eventually know them throughout the block, but not here. Okay, so these are the symbols. Then you have some abbreviations that you need to know. And there's 2. There's abbreviations of the gas phase and abbreviations of the blood phase, which are different, and you'll see how. So the gas phase means these abbreviations are related to the lung. They're somehow related to the lung. Just think of it as gas goes into the lung. So these are gas phase related to the lung. And they're all capital letters. So you will see why I'm mentioning this later, but they're all capital letters. So you have a capital A, which means alveolar. Capital B means barometric. Capital D means dead space. Capital E means expired. Capital E means inspired. Capital L means lung. And capital T means tidal. You don't need to worry too much about the definition or what this is, because we'll go over this in the lecture. Like, all of these concepts are explained very well in the lecture. Just know that this abbreviation means I'm talking about this, because it gets very tedious to like say the whole thing again and again. So we use these abbreviations instead. Now, these abbreviations are gas phase, they're related to the lung, and they're all capital. So please know that. Some other abbreviations, and these are blood phase abbreviations. That means they have something to do with the blood or something to do with the circulatory system. And they're all small letters, if you notice. So how I would relate it is blood is circulatory. So yeah, blood phase. Arterial is small a. Now you see, some of the abbreviations are actually the same, but the difference is that one is capital and one is a small letter. So we see here, capital A means alveolar, and small a means arterial. So you need to be very careful when you're reading these, because it could easily mess you up. Like, it could completely change the meaning of a question if you don't read the abbreviations properly. So small a is arterial, small c is capillary, small c with the little comma on top is called end capillary, and end capillary is the terminal point of the capillary network, which means just the ending of the capillary is the end capillary, quite simple. Ideal is I is ideal, V is venous, and V with the bar on top is mixed venous. Now, I added these definitions even though they were not in the lecture because people get confused between venous and mixed venous. And it's very simple. Venous blood refers to the deoxygenated blood returning to the heart through the veins. So the venous blood is basically, I don't know how to explain it further, but it's deoxygenated blood returning to the heart. The mixed venous blood, which is V with the bar on top, is specifically referring to the blood that has reached the right atrium after circulating through the body's tissues. So yes, they're very similar, but venous just means deoxygenated, but mixed venous means that it has reached the right atrium. That's the difference. And yeah, they're all small letters, and that's all you need to know for the abbreviations and the symbols. So now we're done with the language that we're going to use for this lecture, and we're just going to move towards the actual lecture now. Okay, so just the same thing, please take note of the capital and everything. And then we have some general abbreviations, which is RS means respiratory system, and CW means chest wall. We won't really be using them too much today, but in future lectures, definitely very important. Okay, so the examples, and there's another example here to show you how it makes a huge difference. Capital V is gas volume, and we mentioned this earlier. And small v is venous blood. So you see, even though they're both V, just the fact that they're capital or small makes a huge difference. And now we'll practice a bit. So we have O2 concentration in arterial blood. So first of all, we're going to look at concentration. Concentration is capital C, straight up. It was over here. Concentration of gas in blood is capital C. So we have C, we have small a, because small a refers to arterial, and that's right here, right? Because it says arterial blood, and then it says oxygen, which is just O2. So you have CaO2, and then another example is a fractional concentration of nitrogen in expired gas. Now, there's a lot to take in, but let's break it down. Fractional concentration is F, and it was over here. Fractional concentration is F. Expired gas is E. Where was it? Okay, here, expired gas, E. And then N2 is just the gas that's expired. So FeN2 would be fractional concentration of nitrogen expired gas. And don't worry about it. It might seem like very difficult right now to like learn all of these small letters, but once you go through the lecture, like it'll be like you won't even need to learn it because like it's mentioned many, many times. Okay, so but to practice, here's one. Partial pressure of oxygen in mixed venous blood. So could someone like solve it and like put it in the chat maybe? Partial pressure of oxygen in mixed venous blood. PO2. You're very close, but there's one thing that you're missing, but you're very close. Like I get P is partial pressure and O2 is oxygen. PaO2, again, very close, but it says mixed venous blood. And A, we remember A was arterial blood. Right. So Jumana got it correct. It's PV-O2. And I'll explain why it's PV-O2. So look. So it said mixed venous blood, which means V dash. It's mentioned over here. It said partial concentration, or it said pressure or partial pressure, which is P. And then it said oxygen, which is just O2. So the answer would be PV-O2. So good job, everyone. Very nice. We'll move on to the next one now. Okay, so what is the respiratory system? The respiratory system is basically what we breathe with, right? That's literally, it's that simple. And what does it do? It transports oxygen from outside to our cells, and it also transports carbon dioxide in the opposite direction. That means from our cells to the outside environment. So that's the function of the respiratory system. Very easy, just a filler slide. So now, how does oxygen go from airway to the tissues? So how do we take in oxygen? How do we take in oxygen? That's basically my question. Like, That's the question. And here, what I like to do is, I don't like to remember. I'd rather we go through it in our mind. So when we breathe in, what's the first thing we're doing? We're breathing, right? We're taking it in. And how does this happen? How are we taking air into the nose through the respiratory tract and whatever? The process is called ventilation. So ventilation is basically taking the air into the lungs. Then you have diffusion, and this diffusion is across the lung alveolar capillary membrane. So you know how we have alveoli in the lungs. Everyone knows this. So once the air, this is the fresh inspired air with like a lot of oxygen, like not used at all, it reaches the alveoli, it's going to diffuse. It's going to diffuse across this membrane, lung alveolar capillary membrane. And it's called that because this membrane is between the alveoli and the capillary, which is just outside the alveoli. So this fresh air is going to diffuse into the capillary. Then what's going to happen? Let's just think logically. Now, there's fresh oxygen in this capillary. Obviously, this oxygen is going to go and get distributed in the body because that's the function. Like, that's what the lung is there for. So you have circulation. That's the third step, where the oxygen is going to circulate in the body and then it's going to go to a tissue that needs oxygen. This tissue is asking for oxygen. And then it's going to diffuse again. But this time, the diffusion is across the capillary membrane to the interstitial space. What is I'm sure you guys have already done interstitial space in like F&D. So the second diffusion is from the capillary membrane in the body to the interstitial space. And here's one very important thing that I need you guys to know. The first diffusion, which is diffusion 1, is in the lung. It's across the lung alveoli membrane to the capillary membrane, which is just outside the alveoli. And the second diffusion is in the body. It's across the capillary in the body to the interstitial space in the body. And then what happens to the oxygen now that it's made its way all the way to the tissue? It's metabolized by a cell in the tissue. Okay, so let's just go over it one more time. Ventilation, diffusion, the first time, which is in the lung. Circulation throughout the body. Diffusion the second time, which is in the body, going from the bloodstream to a tissue, and then metabolized by the tissues. The partial pressure of oxygen decreases with each step. So what does that mean? So partial pressure is basically the pressure of oxygen in relation to the entire atmosphere or all the gases together. What's the pressure of oxygen in relation to that? So we see outside at sea level, or like basically in the atmosphere, it's 150 millimeters per millimeters mercury at sea level, right? This is, you don't need to know the values, by the way. This is just to explain to you. 150 millimeters mercury. But when we go through this process of ventilation, diffusion, circulation, diffusion again, metabolized by tissues, we have 1 millimeter of mercury present inside the cell. Only 1 millimeter of mercury of oxygen reaches the cell. And why is this? Well, that's a very good question. And the next like 10 lectures in this block are going to deal with why only 1 millimeter reaches the cell. But basically, to summarize it, it's basically because like the body is not 100% efficient. At every step, there's going to be some loss of oxygen, and only 1 millimeter will reach the cell inside. So from outside to inside the cell, there's a decrease in partial pressure. That's all you guys need to know for now. Okay, so and then we talked about oxygen, but what about carbon dioxide? And you guys are very lucky because you don't need to know anything extra. It's the same thing, but in the opposite direction. So you see how we went from the lung to the body here, the ventilation to in the lung, diffusion 1 in the lung, circulation in the body, diffusion 2 in the body, and then metabolism. It's just the opposite. So the diffusion takes place. So the carbon dioxide diffuses from the cells to the blood, to the capillary. The capillary circulates and it goes to the lung. Well, actually, it wouldn't be a capillary in this case, it'd be a venule, but okay. So the metabolites diffuse into the venule. The venule goes through the circulation, becomes the IVC. It becomes the pulmonary artery, goes back to the lungs. It diffuses across the alveolar membrane. So the carbon dioxide is going from the capillary. The carbon dioxide is going from the venule in the lung across it to the alveoli. And then now we have the carbon dioxide in the alveoli, and it's just going to be excreted by the lung or just like removed. So it's the same thing as oxygen, but in the opposite direction. And the partial pressure of carbon dioxide decreases with each step again, but in the opposite direction, because everything is opposite here. Just remember opposite, opposite. So you remember how oxygen was high partial pressure outside and lower inside the cells? Well, for carbon dioxide, it's higher inside the cells. And as we keep going as we keep moving from one step to the next, it decreases. And the reason for this is the cells are a very small area. Like, do you agree? Like, you can't even see them unless you use a microscope. So the partial pressure is going to be high because the stuff in the cell is very small. It's concentrated. That's why you're going to have a high partial pressure of carbon dioxide. But once you reach each step going outwards, eventually you reach sea level and you have the entire atmosphere, like the whole world, the entire atmosphere to deal with. And that's why it becomes almost zero, like it's negligible. But inside the cell, it isn't negligible because the cell is so small compared to the atmosphere. And the cell is so small in general. And that's why you have the decrease in CO2 in each step. So initially, inside the cell, it's 45. You don't need to remember the numbers again. These are just to show you. Initially, inside the cell, it's high. And then with each step, it keeps on getting lower because you're going to a bigger environment, a bigger atmosphere. Okay, so we're done with this now. This is just a diagram to show you. So remember how I told you the first diffusion takes place in the lungs, across from the alveolar capillary, from the alveolar membrane to the capillary. So this is the alveolar membrane you see over here, and this is the capillary with the erythrocytes in it. Erythrocytes are red blood cells, obviously. So the diffusion would take place at this point. This is the first diffusion. It's going to go from the alveoli into the capillary, and then this capillary is going to go into the circulation. It's going to do diffusion again and go into a tissue in the body, and then that's going to metabolize it, and yeah. So, okay, now we're going to move to respiratory tract structure. Now, to make this very easy for you guys, I'm going to compare it to a tract that most of you are aware of, or like all of you actually, because you did FND. So think of the circulatory system. It starts out huge, like starts out with the aorta, starts out with the starts out with the aorta. It's huge. And then it branches and becomes smaller and smaller. So the aorta becomes smaller, it becomes arteries, and then you have like arterioles and you have capillaries. So think of the same thing, but for the respiratory structure, because at the fundamental level, they perform similar function. And you might say, wait, what? The circulatory system, it transports blood and the respiratory system transports gas. How is that similar? But the similarity lies in what they're doing. So both of them are responsible for long distance transport and exchange of substances. And that makes their structure like similar. So they both start out big and then keep branching and becoming smaller. So the respiratory tract is divided into two parts, and it makes it much easier if you study them in two parts. So you have the upper respiratory tract and you have the lower respiratory tract. So we're going to focus on the upper one. So when we inhale the air, just like think with me for a second, just imagine like you're inhaling air. So where does the air go from? You take a breath, it goes through the nostrils, and then it moves into the nasal cavity. After moving into the nasal cavity, it moves into the pharynx and then into the larynx. So all of the ones that are highlighted in red, those are the parts of the upper respiratory tract. And instead of remembering them, we can just look at this diagram. So let's pretend there's an air here, we're taking it in. These are the nostrils. We're taking them in. Okay, we took them in. Khalas. They're in the nasal cavity. Now it moves from the nasal cavity to the nasopharynx, and then eventually to the pharynx. And then it moves downwards to the larynx. So all of this, nostrils, nasal cavity, pharynx, and larynx are part of the upper respiratory tract. And obviously the nostrils and the nasal cavity together, they form the nose. But just for the purpose of remember that nostrils and nasal cavity are part of the upper respiratory tract. So what's the function of this upper respiratory tract? Like, why is it there? Why do we need it? So it's a very simple function. It has a lot of mucus and it has a lot of blood vessels. And what's the use of this? The blood vessels have a lot of blood, and this blood is warm because blood is just warm in general. It's a property of blood. So the blood warms and moistens the mucus, which in turn warms and moistens air before it flows into the lower respiratory tract. So basically, the blood warms the mucus inside the upper respiratory tract, and this mucus in turn warms the air. When it goes in, it warms the air. And why does it need to warm the air? is because the lower respiratory tract, it's a deep tissue in the body. You don't want to disturb it. You want to keep it like at a particular temperature, and you don't want to ever disturb this temperature. And that's why the mucus is going to warm the air that we're breathing in. Another function of the mucus is it traps inhaled particles. So when you're breathing, you might take in dust, you might take in some like smoke, whatever, and this is all going to be trapped by the mucus and eventually expelled. So yeah, that's the upper respiratory tract. If anyone has any questions, by the way, you can put it in the chat. This is the diagram. So quick revision, we can just look at it. And then we have the lower respiratory tract, which is I want you to think of a tree trunk right now, and the tree trunk that's dividing and becoming its roots. So it starts off as a tree trunk, but then it divides and becomes roots. And the trunk, in this case, we're talking about the trachea. Okay, so the trachea is a continuation of the larynx. The larynx is this part over here. So when this continues downwards, we'll have the trachea, and this is a better picture here. So the larynx continuing downwards to the trachea. Then the trachea divides multiple times, like a root divides. Like, you see a root dividing into many parts. That's how the trachea divides. The first division, it makes two main bronchi, a right bronchi and a left bronchi. So let's look at it in the diagram. Here's the trachea. It divides into two. This is the right one. This is the left one. Okay? Then the main bronchi, they don't stop dividing. They keep dividing. And they divide 15 times. You guys need to remember the number, and you need to remember every number on this slide. I'm sorry, like I don't make the rules, but you need to remember every number on the slide. So the main bronchi divide 15 times. And once the main bronchi divide 15 times and they reach the size of 1 millimeter diameter, they're called bronchioles. And this number, they might ask you once the bronchi becomes dash mm, it's called a bronchiole. So you need to know the number. So the bronchioles are 1 millimeter, and the bronchioles are formed when the main bronchi divide 15 times. The bronchioles, do they stop dividing? No, they don't. The bronchioles divide again, and they divide 12 times. They divide 12 times, and then they become alveoli, which are very small sacs, about 0.5 millimeters in diameter. Again, please remember the number, guys. Let's go to the diagram to make it way easier. So this is the trachea, two divisions, right and left. The right bronchus divides into bronchioles, which you see over here, bronchioles, 12 times. The right bronchus divides 15 times, and then it becomes a bronchiole. The bronchiole is 1 mm in diameter. The bronchioles now will divide 12 times until they become these clusters of alveoli, and the diameter is 0.5 mm. So please remember these numbers. And the alveoli are very important. You'll study why. And this is known as the gas exchange region or the respiratory zone, because this is where the actual gas exchange takes place. And we'll study more about this in the lecture. So just remember, it's called the gas exchange region or the respiratory zone, because this is where the actual gas exchange takes place. Okay. One small thing before we move to the next part. How does air move in the respiratory system? So in the upper respiratory tract, in the trachea, in the bronchi, and in the bronchioles, air moves by bulk flow. Bulk flow, which means the air just moves along with the air currents. Okay, like air would move outside the body, it moves inside the body the same way, by currents, bulk flow. But in the alveoli, which is the gas exchange region or the respiratory zone, air moves by diffusion. Air does not move by bulk flow. Please remember this. Air moves by diffusion. And where does it diffuse to? Can anyone answer in this chat? Someone answer where the air diffuses to. If you have air in the alveoli, where does it go? Where does it diffuse to? We mentioned this earlier in the lecture. Can someone answer in the chat? To the blood capillaries, exactly. So the air diffuses to the blood capillaries, which are just outside the alveoli. So yeah, once again, let's just go over it real quick. Upper respiratory tract, trachea, bronchi, and bronchioles, the air moves by bulk flow. Basically, the entire respiratory system, except the alveoli, the air moves by bulk flow. But in the alveoli, it moves by diffusion and diffusion only. Please don't forget this. Okay, so the entire respiratory tract, except the alveoli, have a specific name. They're called the conducting airways. And why are they called conducting airways? It's because the air moves by bulk flow in them. So everything except the alveoli is a conducting airway. Remember this. Okay, so we have a quick summary now, so we can recollect our thoughts. So what's the structure, like how does it go? It goes from nostril, the air, when you breathe in air, it goes from nostrils to the nasal cavity, to the larynx, to the pharynx, to the trachea, to the main bronchi, and then the main bronchi divide 15 times, I mentioned it here, 15 times, and it become bronchioles. Bronchioles are 1 millimeter in diameter, and then these bronchioles divide 12 times, and they become alveoli. That's everything that we mentioned in a summary here. Okay, so we're gonna move to the next slide. This is like the first actual topic which is important and needs to be explained. Dead space and gas exchange space. So the airway has 23 generations. And what is a generation? A generation is basically a branching. Like when you branch, that's one generation. So the airway has 23 generations. The first 16 are conducting airways. And what are conducting airways? We just mentioned it. Can someone put it in the chat? What are conducting airways?
Basically, where we bring the oxygen from the upper atmosphere towards the lung without gas exchange happening.
Perfect. That's literally perfect. That's exactly what conducting airways are. It's where we take the air and bring it towards the alveoli by bulk flow. And there's no gas exchange taking place. It's just moving it towards the alveoli where the actual gas exchange takes place. The next 7 are gas exchange regions. And this is a very nice diagram to help you out real quick. So we have the first 16, you see, these are all conducting airways. So this is all conducting airways. The last 7 are part of the alveoli, basically, and that's why they're gas exchange regions. So this thing that we see here, these are all part. This isn't an alveoli itself, but it's all transitioning towards an alveoli. And the last 7 from the respiratory last 6 actually, the last 6 from the respiratory bronchiole to the alveolar sac, these all they actually can participate in gas exchange, and air moves by diffusion and not by bulk flow here. Okay, so what's anatomical dead space? The first 16 generations, which is basically the entire respiratory tract except the alveoli, do not have any exchange of gases between inspired air, that means the air we took in, and the blood. So there's no exchange. All they're doing is transporting the gas from outside to the alveoli. So that's the entire function. And this is called anatomical dead space. Anatomical because it's present like anatomically, like you can't change it. It's like present in everyone. And you'll see later there's a different type of dead space as well. So anatomical dead space is the first 16 generations which transport the gas towards the alveoli, but there's no exchange of gas in them. The next 7 generations is where the fun stuff happens. And this is where we have actual gas exchange, which means the next 7 generations are the ones where there's exchange of oxygen, exchange of carbon dioxide, and then all of this good stuff is happening in the last 7. And this is the gas exchange region. The gas exchange region is basically the alveoli. It's not exactly the alveoli because there's respiratory bronchioles, and then there's alveolar sacs, and then there's the actual alveoli. But in general, we can just call it the alveoli. So the gas exchange region is where the alveoli takes place. The gas exchange region is the alveoli, and this is where actual gas exchange takes place, like oxygen, carbon dioxide, and all of that. And how much gas exchange region do we have, like a normal human? So basically, I'm asking you, what's the surface area of alveoli in our body? Because that's where gas exchange takes place. And it's 1 meter square per kg. This is not very important. It's low yield. So if you don't want to focus on it, you don't need to. This part, the last sentence. Before that, it's very high yield. So 1 meter square per kg is how much gas exchange area we have, and the average thickness of the alveolar capillary is 1 to 1.5 micrometers. Now let's move on to the next slide. So we talked about anatomical dead space. Now let's talk about physiological dead space. Let me just read it out for you, and it's very self-explanatory, inshallah. Some areas of the gas exchange region, which is the alveoli, may be collapsed or not perfused. Not perfused means there's no blood supply to them. Hence, even though in theory they should contribute to gas exchange. They do not. Instead, they're similar to the anatomical dead space where no gas exchange takes place. So these areas, which means the damaged gas exchange regions or the damaged alveoli where there's no gas exchange, these areas, along with the anatomical dead space together, are called physiological dead space. So physiological dead space is anatomical dead space plus the non-functioning gas exchange region. And why are they not functioning? They're not functioning because they're not perfused or they may have collapsed. Okay, that's physiological dead space. Very important concept. Now we're coming to this next part, which is it's a kind of like a transition, but the lung volume at the end of normal expiration. So expiration is when you're breathing out. So you're taking a normal breath out, like you're taking a normal breath out. You have 3 liters of oxygen, 3 liters of air left in your lungs. And this is called functional residual capacity. You don't need to know the name right now because the next part of this lecture is all about the names. But just remember, when you breathe out, you have 3 liters of air left in your lungs when you breathe out. And 5% of this, which is 150 ml, is dead space volume. So the dead space is 5% of the amount of air left in your lungs after expiration. And the rest, which is the rest of the 95%, or the 2,850 ml, is in the gas exchange region. So once you breathe out, 5% of the air that's left in your lungs is going to be in the dead space. So basically, what this helps us measure is the dead space volume. So the dead space volume for a normal person is around 150 ml. And another very important thing is that lung volume changes upon inspiration. So you might think that, oh, my lung volume is 5 liters. But no, that's not right. Your lung volume is changing. It could be 2 liters and it could be 7 liters. And it depends. So when you inspire, you're taking in air. So your lung volume is increasing. When you expire, you're breathing out air. Your lung volume is decreasing. And the change is in the alveolar space, in the gas exchange region. That's where the change in volume is taking place. There is no change in volume in the dead space. The dead space is always going to be the same. So the dead space is 150, we mentioned here. So now when the lung volumes are changing, the dead space is not going to change. The only volume that's going to change is the gas exchange region or the alveoli. So you see this number, 2,850? When we inhale, this number is going to increase. The gas exchange region, this number is going to increase. This number is not going to change. 150, that's dead space volume. Like, you can't change that. If you're exhaling, this number may decrease. It may become 2,500, but this number is never going to decrease. It's going to stay the same. So dead space volume never changes. Only the alveolar volume or the gas exchange volume changes. Yeah, and then this, I feel like every batch has this as a question on their final. And here's the question. It's super simple. You would never believe that people even get this wrong. So physiological dead space is anatomical dead space plus non-functioning alveoli or non-functioning gas exchange region, right? Like we mentioned this over here. Physiological dead space is anatomical dead space plus the gas exchange region that's not working. So physiological dead space can never be smaller than anatomical dead space. It can only be equal to or greater. And if you think about this mathematically, you're going to say, of course, that makes a lot of sense, but you won't believe that a lot of people actually get this wrong. So the physiological dead space is anatomical dead space plus non-functioning alveoli. So how can it ever be smaller than anatomical dead space? Like you have this, and then you have this plus this. Even if this is 0, these two are going to be equal. This and this are going to be equal, even if this is 0. But usually this is not 0. So physiological dead space is more than anatomical dead space because you're adding something, right? It's never smaller. And then we have tidal volume, which we'll take in the next lecture as well, but I'll just go over it here. And this is the volume of a normal breath. So like you're breathing right now, like we all are. You're taking in a breath. This normal breath is 500 ml, and that's the tidal volume. And remember what we said, the physiological dead space. The dead space never changes. And what's the volume of the dead space? Like we mentioned this earlier. Can someone write it in the chat? What's the volume of dead space? The dead space in the respiratory system, how much? Like how many ml approximately? It was in the previous slide. 150 ml, 150 ml. Yeah, that's correct. So 150 ml, when you take a breath in, 150 ml is going to be in the dead space because the dead space is 150 ml. So 150 ml is going to stay there. And the rest of the breath, which is 500 minus 150 equal to 350, is going to reach the VA. Now, what's the VA? Come on, guys. We did the symbols and everything. Someone tell me what VA means.
Articular volume.
Can you repeat that?
Articular volume.
Uh,
The volume
no,
in our
it's
in
volume. It's not arterial.
no, not arterial. Sorry, I mean alveolar
Alveolar.
volume.
Exactly.
Yes.
It's alveolar volume. So the rest of the gas, which is 500 minus 150, is going to reach alveolar volume. The 150 is going to stay in the dead space because we mentioned over here that the dead space is 150 ml, right? Also, just real quick, guys, I want to tell you that everything that I'm saying is in the slides, like everything. So even if you were to go over the slides later, you don't need to listen to the recording. Just go over the slides. Everything is in the slides. And the second thing is, if I do say anything outside the slides, I'll add it later in the notes and I'll send you a new one. And other than that, just like, that's it. That's all I wanted to say. We saw this diagram. The first 16 generations are the ones that are like conducting airways. There's no gas exchange in them. The next 7 are the ones where gas exchange actually takes place. And this is the gas exchange region, the next 7, which is these, the alveoli. The first 16, which are the conducting airways, no gas exchange, just transport. Okay, so now we're going to the easier part. Just give me a sec. So we're moving to airway epithelium, all right? Now there's 3 types of 3 different classifications. We have the bronchi, which comes from the trachea when it divides. We have the bronchioles that come from the division of the bronchi. And then we have the alveoli, which come from the division of the bronchioles. Can everyone agree with me on this? Like, there's no confusion or anything, right? Can everyone agree? Like, if you agree with this, just like yes in the chat, or just say yes in the chat if you agree. If what I'm saying makes sense. Okay. Yeah. Okay. So the bronchi, the epithelium, this is basically like the histology. We'll focus on it a little bit, but you'll study more about it in histology. So the bronchi contain cartilage, which makes them fairly rigid, and smooth muscle, which can make them alter their diameter. So the bronchi have cartilage and smooth muscle. They also have mucus, and the mucus is produced by goblet cells and mucus glands. Okay? The epithelia has cilia on its luminal surface. Now, what's the luminal surface? The luminal surface is the side of the cell that's facing towards the lumen. So, like, one sec. Let me see if we can draw it. Okay. So, this is the trachea. If you're looking at it from like, wait, that's bad. Just give me a sec. So we're looking at the trachea from like up top. This is the trachea. This is the lumen of the trachea. So this cell, which is present towards the lumen, is called a luminal cell. Okay, so this cell is a luminal cell, and this luminal cell has cilia for the bronchi, and it also has mucus produced by goblet and mucus glands, and it has cartilage and smooth muscle. Now we move to the bronchioles. We're done with the bronchi. The bronchi divided like 15 times, and they became bronchioles. The bronchioles have no cartilage, like no cartilage, but they have smooth muscle. Okay, so no cartilage, but smooth muscle. They also have no glands, so they have no mucus. Okay, no glands. Like this goblet cell mucus gland, no, it's not there. The epithelial cells are smaller and carry cilia only in larger bronchioles. Now, what are larger bronchioles? Like we know there's bronchioles, what are larger bronchioles? So when we go here, you see there's 2 types. You don't need to know this, by the way. Like this is just like I'm telling you. There's larger and smaller bronchioles. So you know how bronchi divide 15 times and they become bronchioles? So maybe by the 12th division, you have a large bronchiole. And then by the 15th division, you have a small bronchiole. So the larger bronchioles have cilia, but the smaller ones don't in bronchioles. There's no glands, there's no cartilage, but they have smooth muscle. So just remember these classifications. because they're important, and we did have a question about this in the final. Alveoli. Now, alveoli are formed when bronchioles divide 12 times. We already did this, right? So the type of epithelium that lines an alveoli is alveolar epithelium type 1. Okay, finish. Like, that's it. Alveolar epithelium. Like, it could not get easier than this. It contains no smooth muscle or cartilage. Can anyone tell me why it contains no smooth muscle or cartilage? In the chat, please type
Because
that.
gas exchange, so you
Yeah,
cannot do
yeah,
gas exchange with muscles and cartilages.
yeah. That's exactly, like, you're right. Because of gas exchange, we want gas exchange to take place in the alveoli. We don't want anything to obstruct this gas exchange. So we're trying to keep it only epithelium, only epithelium. So there's no smooth muscle, no cartilage, no mucus glands, no anything, no cilia, nothing. Just epithelium, very thin epithelium for the gas exchange. Now, bronchi and bronchioles and their cilia form, oh, I forgot to mention it here, but they form something called a mucociliary transporter. Let me write it down here. Muco, oops, I'm very slow at this. Mucociliary. Wow, it's hard to write with the touchpad. Okay, mucociliary. I'll write this in the slides when I send them to you guys. Bronchi and bronchioles and their cilia form a mucociliary transporter. And basically what this does is the cilia, they beat upwards and they clear the lung of any harmful particles. So let's say you have some dust, you have some smoke stunk in your lungs. These mucociliary transporters are going to beat and remove this. It's going to go upwards. So basically the mucociliary transporter just like removes particles from the bronchi and bronchioles. Now we have an alveolar macrophage. So in the bronchi and bronchioles, this mucociliary transporter is taking care of like cleaning. What's taking care of the cleaning in macrophages? Sorry, what's taking care of the cleaning in alveoli are the alveolar macrophages. And what they do is phagocytose dust and other particles and keep the alveoli clean. And here's a picture of an alveolar macrophage. Like this is the alveoli, and then it's just present here eating up dust and other particles that are harmful to us. So why do we have the dead space? Like, what does it do for us? So first thing, it conducts the air to the air exchange, to the gas exchange region. So it basically transports the air to the gas exchange region. And we already discussed this, the transportation. It warms the inspired gas, which happens in the upper respiratory tract. If you remember, we had these blood vessels and mucus, and the blood vessel warms the mucus, and then the mucus warms the air, and then this whole thing happens in the upper respiratory tract. So it warms the inspired gas, it increases the humidity and softens the air, it cleans the inspired gas from dust and particulates. All of these three steps happen in the upper respiratory tract. And then the last function is defense against microbes via IgA and IgG. These are antibodies. You probably don't need to know exactly which antibodies, but just remember that the dead space has antibodies to protect us against microbes. It's that simple. Okay, so guys, I have very good news. We're done with the first lecture. And this is, you can ask me anything if you have any doubts. If you want me to go over a slide again, if you just want to go over a slide so we can explain it better, you can do that. And we can take like a 2-minute break if you guys want to. If you don't want to break, just let me know in the chat that if you don't want to break, and we'll just continue and trying to finish it as soon as possible. But if you want to break, that's cool too. All clear. Okay, that's very nice. So okay. We'll take a break for 2 minutes. The time is 7:49. We'll be back at 7:52. So actually 3 minutes. And if anyone has any doubts, I'm here. I'm waiting. And I'm going to take any questions right now. Anything. If you want me to explain a slide, like a whole slide, I'll explain it. But we'll be back at 7:52, guys. Thank you. Extra. We took 2 minutes extra, but we let it slide. We're going to continue now. So we're done with the first lecture, which was Introduction to Pulmonary Physiology. We're going to go to the next lecture, which is lung volumes. Much easier. There's only one big concept that you need to understand, and the rest is definitions, which is easy. So what is lung volume? It's the volume of air in your lungs. That's literally as easy as it can get. It's lung volume is the volume of air in your lungs at a particular time. And as I said earlier, lung volumes are not constant. They keep on changing. So when you inspire, you're increasing the lung volume. When you expire or like exhale, you're decreasing your lung volume, right? So now we're going to talk about maximal expiration. Maximal expiration means you expire more than you normally would. So in a normal in a normal expiration, you expire like, okay, like you expire just like a normal person. But in maximal expiration, you force yourself to expire more air than normal. And even then, the lung does not empty completely. So even on maximal expiration, the lung does not empty completely, no matter how hard you try. It still has 1.5 liters of air left. And this is called the residual volume. The volume left at the end of maximal expiration is residual volume. And what's maximal expiration again? It's trying to expire as much as you can. With normal exhalation, we do not empty the lungs to this volume. Like when we're talking about normal now, not maximal, like just normal, like a normal person would do. We have 3 liters of air left in the lung. And this 3 liters is divided into 2 parts, okay? The first part is the residual volume, which we already took. This one, residual volume, this one, they're the same. So when we expire as much as we can, we still have residual volume left, 1.5 liters. If we expire normally, we have residual volume left. In addition to this, you have expiratory reserve volume, which is 1.5 liters as well. So these two values together make up the 3 liters of air that's left in the lung once you do a normal exhalation, normal expiration. Okay. So the expiratory reserve volume, what is it? Can someone like mention like what it is? Like what is the expiratory reserve volume? Like what do you think? Because I haven't mentioned it yet, but what do you guys think? Expiratory reserve
It's
volume. What is it?
basically the volume that it's left after you're just doing minimum expiration. So after finishing like expiring normally, we're gonna have expiratory reserve volume and residual volume.
Okay, yeah, you're correct. So the expiratory reserve volume is basically the amount that's left in addition to the residual volume when you do a normal expiration. So this is the amount of air that you could expire if you did it forcefully. If you wanted to forcefully remove it, you could remove this 1.5 liters, expiratory reserve volume. Okay. And we mentioned tidal volume earlier in the previous lecture. It's basically the amount of air that you inhale or exhale normally. And it's about 0.5 liters. So if you're breathing normally, breathing in and out, you're inhaling and exhaling 0.5 liters each time, and this is called tidal volume. And now we have something called inspiratory reserve volume, which means, you know how we breathe in normally? We do the tidal volume, 0.5 liters. Well, what if we wanted to breathe in more? We wanted to breathe in extra. We want to take a deep, deep, deep breath. And this is where inspiratory reserve volume comes in. This volume is when you breathe in extra more than you would normally. This is inspiratory reserve volume, and it's around 3 liters. It's not actually 3 liters, it's 2.5 liters. But once you're taking the inspiratory reserve volume, you're also taking tidal volume, which is 0.5. So the 0.5 and 2.5 get added, and you have 3 liters total. But the inspiratory reserve volume is 2.5 liters. This is the extra volume that you can breathe in if you wanted to. You don't normally, but if you wanted to, you could. So I have a question for you guys. Let's say we have a person that is completely that has exhaled normally, like a normal exhalation, and then he takes a deep breath in. So normal inhalation. What's the difference in the lung volume between these two cases? Like how many liters would be the difference be? It's the same person, the same lung. In the first case, he's exhaling, so he has this volume in his lungs, X, and then he's inhaling, which changes the volume. What's this change? How much is the change? Can someone answer? It's a bit tough, but like, I would be really happy if you guys could answer this. In the chat, someone. No one? It's okay if you guys don't know, because like it's a very hard question. Okay, so the answer is 0.5 liters. How is it 0.5? How? We said during normal breathing, we inhale and exhale about 0.5 liters, right? So we exhaled. Plus, we have a lung that's exhaled. Let's say the volume is X now. Okay? Volume of this lung after exhalation is X. Now we have inhalation. And what's normal inhalation? Is 0.5 liters. So we add 0.5 plus 0.5. And this is the volume after normal inhalation. So that's why the answer is plus 0.5. I hope you guys understand. If you don't understand, by the way, just tell me in the chat and I will stop and I'll explain again, as many times as you want. This is the most helpful diagram. Okay, you want me to repeat? Okay, just one second. I'll go back. Okay. You want me to repeat why it's 0.5?
Yes.
Okay. So listen, we have a lung. We have a person. He's a normal person. Everything's normal with him. He exhales his air. He removes the air from his body. And now let's assume that the volume left in his lungs is X liters. So he has X liters of air left in his lungs after the exhalation. What happens after we exhale? We inhale, right? Like that's the cycle of life. So we take air in. We take air in. And how much air do we take in? It says in the first line, during normal breathing, we inhale/exhale about 0.5 liters. So assuming this is a normal inhalation, and it does say normal inhalation over here, he's going to take in 0.5 liters. 0.5 liters, right? This 0.5 liters is going to be added to the volume that's already in his lungs. His lungs already have X liters after the exhalation. This 0.5 liters is going to be added to the X. So you're going to be left with X plus 0.5. So what's the change? The change is X plus 0.5 minus X, because we already had X. And that leaves us with 0.5. Do you get it? If you don't get it, I'll explain again. Okay, that's nice. Okay, so this diagram is very helpful and it's going to sum up everything we did. We have residual volume. This volume does not change under any circumstances. This can never leave the lungs. Even if you try your best, it can never leave. You have expiratory reserve volume. This volume will only leave the lungs if you force it to. Okay? If you tell it, leave, if you breathe out super hard, then it's going to leave. Otherwise, if you're doing a normal breath, it's not going to leave. Okay? Then you have tidal volume, and this is the normal inspiration, normal exhalation is tidal volume. So if you were breathing in or breathing out normally, this is the tidal volume that would be there. And if you're forcing yourself to breathe out, then expiratory reserve volume would also leave. And then you have inspiratory reserve volume, which is if you force yourself to breathe in extra air. Expiratory reserve volume is breathing out extra air. Inspiratory is in. Just remember, as inspiratory, in, you're breathing in air, like in, and expiratory is outwards, like expire, remove it. So inspiratory reserve volume is the excess air that you could breathe in if you wanted to. You usually don't, but you could if you wanted to. So let's go over the volumes real quick. Residual volume. Can anyone tell me what's the normal residual volume for a person? A normal healthy person, what's the residual volume? 0.5 liters. Excellent. Then expiratory reserve volume. What's the normal expiratory reserve volume for a normal person? Anyone? Anyone? No? Okay, so it's 1.5 liters, and we mentioned it over here. Expiratory reserve volume is 1.5 liters because it's a part of the normal, it's going to be in the lungs if we do normal exhalation, but this will be removed from the lungs if we do excessive respiration. We have tidal volume, which is 0.5 liters as well, and this was mentioned over here. Tidal volume 0.5 liters.
Can you go back to the residual volume, please? In the residual volume, someone said yeah, someone said in residual volume that it's 0.5 liters, and you said it's correct. But then if you go back, it says 1.5 liter, the residual volume here.
Here. Oh yeah, okay,
Yeah,
that was my mistake. It's not 0.5, it's 1.5. I totally forgot that. I apologize for that, but it's 1.5 liters. The residual volume is correct. It's 1.5. So this thing is 1.5. This
so
expiratory reserve volume,
it's
it's also
1.5.
1.5. The tidal volume is 0.5, and the inspiratory reserve volume, what is
It's
it? Can
2.5 بس يعني 3 كمان.
2.5, because then you add the tidal volume, it becomes 3. So this whole thing together would be 3. Okay, so let's move on. What device is used to measure lung volume? So how can we measure lung volume? We're talking about expiratory, inspiratory, whatever. How do we measure it? So we measure it with a spirometer, and it's just to measure lung volume. How does it work? It's a gas container with a variable volume that can be recorded. So it's connected to a patient through a tube, and when the patient breathes, there's a change in lung volume, and this change in lung volume can be recorded on the spirometer as inversely proportional to what's happening in the lung. So if lung volume decreases, that means the patient's breathing out, the spirometer value increases. If lung volume increases, the spirometer value decreases. So basically it works in an inverse way. Like what the patient is doing is going to show you the opposite. So if the patient's lung volume is decreasing, it will show the spirometer value increasing, and vice versa. And the very important thing is a spirometer can only work if you have a change in lung volume. So every change in lung volume is measured by the spirometer. So what can we measure using spirometer? We can measure VT. Can anyone tell me what VT is? In the chat, please. No one? Tidal volume. Exactly. It's tidal volume. So VT is that we can measure tidal volume. We can measure the inspiratory reserve volume and the expiratory reserve volume. We cannot, however, measure the residual volume. And why? Why can we? Why? Why? Why not? And the reason is because to measure, like it's mentioned here, for a spirometer to work, we need to have a change in the lung volume. It says here, if connected to a patient through a tube, changes in lung volume of the patient can be recorded. Okay, but the residual volume, if you guys remember, it can never change. It can never come out. It's always in the lung. The residual volume of 1.5 liters is in the lung. It can never come out, no matter how much you force it. So it can change. If it can change, the spirometer cannot detect it. It says it in the definition. Changes in lung volume, and there is no change when you're in the residual volume. Okay, so how do we measure residual volume? And like you're like, okay, you can't measure it, but like how? There has to be a way, right? And yes, there is. It's the inert gas dilution method. And I want to explain it on the diagram, and then I'll come back to this. So it's similar to a spirometer, but instead of just air, we have an inert gas, helium in this case. So we have this spirometer, we have the helium inside here, and we have the lungs of the patient, and it's connected by a tube, right? So we ask the patient to maximally exhale. So the patient is forcefully removing air from his lungs. So what volume of air is going to be left in the patient's lungs if he's removing forcefully? How much is going to be left? Like how many liters? Can someone answer?
1.5 liter. If he's removing
Yes.
everything.
Yes. 1.5 liters or residual volume will be left if he's removing everything, because that you can never change. So now the patient has 1.5 liters over here, right? Can everyone agree with me on this? He has 1.5 liters here, and let's say you have 5 liters of 5 liters of air in the spirometer along with some helium, and this is closed. So right now these are two separate systems. This is system 1, which is 5 liters, and this is system 2, which is 1.5 liters. Now we ask the patient to exhale. He exhaled. He has 1.5 liters left. We'll open this stop. This stop will open it. So the helium can go here. And these two systems, 1 and 2, they'll get joined because the stop is removed. So this is one system now. These two are joined. And so the total volume, instead of being 5 and 1.5, is 6.5. Okay? And the helium is going everywhere. Now, why is this important? Why are we saying all this? Because initially the helium had a concentration. It had a fractional partial pressure. Let's say the helium was 10% of the air. So the 5 liters, 10% of it, 10% of it was helium, right? Now, when we open the stop, this becomes a big system, 6.5 liters. It's more than 5 liters. So this is going to decrease. The concentration of helium is decreasing, but the amount of helium is going to stay the same. So the amount of helium is the same. It's not going to change. Like, I want you guys to understand this. It's very important. Let's say there's 20 molecules of helium in this barometer, and its concentration is 10%. That means 10% of the spirometer volume is helium. But when we open the stop, these 20 helium molecules are going to be spread into 6.5 liters now instead of 5 liters. So it's going to decrease. Its concentration, its pressure, its partial pressure is going to decrease. It's going to become like, let's say like an example. All these numbers are examples. Then none of them are correct. 7%. Let's say. So now we have a 7% helium concentration in this case when the stop is open, and this is one system, and we have a 10% concentration in this case when the stop is closed, and these are two separate systems, right? But as we mentioned earlier, the amount of helium is the same. If there's 20 here, there's 20 here. None of the helium are going to disappear and none are going to be added, okay? So now this helps us find the residual volume because let's say we have 10%, right? So 0.1, because 10% is 0.1 out of 1, into 5 liters. Okay? Now you're going to be like, why are you multiplying? I'm just trying to find out the number of helium molecules. We have the concentration and we have the total volume. So I'm trying to find out the partial pressure. And this is something you've obviously probably done in like high school. So 0.1 into 5, right? And then over here, again, we're trying to find the concentration. It's 7%. It's 0.07 instead of 0.1. And the residual, and we have here like 6.5, right? So we're going to multiply it by 6.5. And this is just an example. So you know it's 1.5. But in real life, this number is not 1.5. It could be 1.3. It could be 1.4. It could be 1.7. And that's what we try to find using this method. Okay, real quick now. We have a spirometer filled with some air, let's say 5 liters. We also have some helium within this spirometer, let's say 0.1 F, which is fractional concentration. It's the same as saying 10%. This spirometer is connected to a man. However, the valve of the spirometer is closed, meaning that the man and spirometer exist as separate entities, which means this valve is closed. This is system 1, this is system 2. They're completely separate. At this point, the amount of helium within spirometer is 0.1 multiplied by 5. As I said, we're trying to find the partial pressure, or like how much helium there is in molecules. So we multiply the concentration by the total volume, and we get 0.1 multiplied by 5. Now, before we open the valve, we ask the patient or the person to completely expire. That is, expire the expiratory reserve volume, which is what he was keeping, but he can remove it forcefully. He removed this, and now there's only residual volume left in the lung. We now open the valve and allow the two entities to merge and become one. So these two entities become one big system. This increases the volume of the system to 5 liters, from 5 liters to 5 liters plus the residual volume. So as I told you, in real life, we don't know this is 1.5. In real life, this is just residual volume to us. Okay? This is just residual volume. And this is 5 liters. We know this value. We know this is 5 liters. We don't know this is residual volume though. So when we open the system, the total volume is 5 liters, which is this, plus residual volume, which is over here in the lungs. Okay? Due to this increase in the volume, the fractional concentration of helium will also change. Let's say it becomes 0.05 from 0.1. However, the total amount of helium will remain the same. So the amount of helium molecules by themselves don't change. They remain the same, but the concentration changes. because you're increasing the volume, right? Concentration, if you remember, is how much of like the volume of something divided by the total volume, right? So the concentration of helium is amount of helium divided by total volume of all the gases. So if you're increasing the total volume of the gases from 5 liters to 5 liters plus the residual volume, the concentration is going to decrease, right? And that's how we got this number 0.05. And all of these numbers are just made up. So I wanted to give you an example that you could easily understand. So therefore, at this point, the amount of helium within this parameter is 0.05 multiplied by 5 plus RV. We're using the same formula as over here. We're multiplying the concentration by the total volume. But wait a second. We said that the amount of helium is constant. So 0.1 multiplied by 5 should be equal to 0.05 into 5 plus the 5 plus residual volume. Like these two things should be equivalent. And why should they be equivalent? Because we said that the total amount of helium stays the same. It never changes. Only the concentration can change. And now we can solve this equation and find the residual volume, okay? And we'll do an example for this. I explained this, and I feel like it becomes very simple with this. But if someone doesn't understand, please tell me, because this is like one of the most important things in the lecture is this. So if someone doesn't understand, please tell me, and we'll go over it again. If you do understand it, please solve this question. And once you get it, you can tell me the answer in the chat. Try and solve this question. So we have a spirometer volume, 1.5 liters, which is this. This volume is 1.5 liters instead of 5. It's 1.5. The helium concentration is 10%. So 10%. After connecting to a patient and opening the valve, so they connected to a patient, open the valve, the concentration of helium becomes 5%. So what's the residual volume of the patient? Tell me. Use this kind of logic, the one I use over here. Like the concentration, the total amount is concentration multiplied by total volume. That's the amount of helium. And the helium does not change. So can someone...
There is a specific formula for it.
Yeah, but
Like,
you don't need the formula. Like if you just understand the concept, you never need to use the formula. And that was going to be my next step. Here. I have the answer here, but you do not need the formula. You do not, like, yes, there is a formula, and if you want, you could just remember it. But this is so much easier than remembering a formula. You just remember that the helium concentration multiplied by the total volume is the amount of helium. And the amount of helium never changes. It's the same in this case and in this case. So you multiply these two, and then they're equivalent to each other, right? Like this. 0.1 multiplied by 5 is equal to 0.05 multiplied by 5 plus RV. These two values are equal. So using that, you could find RV, which is the residual volume. So could you do it? Can anyone do it? Like in the chat? I guess no one wants to do it, so I'll just show you how to do it. You do not need a formula, by the way. I solved all of these questions without a formula. So according to the question, the initial volume is 1.5 liters, right? And the initial helium concentration is 10%. This is in this spirometer. The final volume is 1.5 liters plus the residual volume. This happens when we open the valve. This valve is open. So this becomes one system, 1.5 liters, which is over here, and then the residual volume, which is in the lungs, which we're trying to measure. We're trying to find it. The final helium concentration is 5%, and that was given in the question. So the helium amount is the same both initially and finally. So the total amount of helium is the same. The only thing that's changing is concentration. Please, 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 please remember this. So we have 1.5 multiplied by 0.1, which is over here. 1.5 multiplied by 0.1 gives us the helium in this case, which is the first case. And then we have 1.5 plus RV multiplied by 0.05, which is the second case. Right? And the amount of helium should be the same. So technically, these two are equal. And we can just solve this equation, and we get 3. So we get the residual volume as 3 liters. Okay? It's very simple. Just solve this. Like in ExamSoft, you're going to have a calculator, or you can just use a calculator at home to solve this. Does everyone understand this concept, inert gas dilution method? It's like one of the most important things in this lecture. If you don't, please let me know, and we can go over it. If you understand it, just say yes in the chat. And we'll move on to the next thing, which is also the last thing in this lecture, or one of the last things. Okay, that's amazing. Thank you, guys. lung capacity is basically the sum of two or more lung volumes. So you know how we had inspiratory reserve volume, expiratory reserve volume, and all of that stuff. If we add them together, we get lung capacity. So we have 4 types, and I have a diagram to make it much easier, but we'll go through them like this. So we have inspiratory capacity. So just think logically, inspiratory capacity means how much you can breathe in. Like just by, if you know English, you can know that. So how much can we breathe in? We can breathe in the tidal volume, which is normal, and then we can force ourselves to breathe in extra, which is inspiratory reserve volume. So the inspiratory capacity is inspiratory reserve volume plus tidal volume. The functional residual capacity is the amount of air that's left if you do a normal exhalation, no excess exhalation, nothing extra, just normal. That's equal to the expiratory reserve volume plus the residual volume. This is what would be left in the lungs if you did normal expiration. Now we have vital capacity, and this is very important because it's the largest breath that you can take. So let's like have a situation now. There's a person who exhaled like maximum exhalation, like he removed all the air from his lungs. Like there's only the residual volume left. Now this person is breathing again. He wants to inhale. How much is he going to be able to inhale? He can inhale the tidal volume, inspiratory reserve volume, and expiratory reserve volume. And let me just rearrange this so you can get it easily. So he breathed, he has nothing in his lungs except residual volume. This is the only thing that he has in his lungs, right? Now, when he breathes in, the first thing that he's going to replenish is the expiratory reserve volume. He's going to add it. Okay, done. Expiratory reserve volume done. Now we have the functional residual capacity. These two things are back. Then we're going to add the tidal volume. He's going to take the tidal volume, which is the normal breath a normal person would take. And then he's going to take inspiratory reserve volume because he's really forcing himself. He wants as much air as possible. So all 3 of these together are the vital capacity. And this is the largest breath that you can take. Then we have total lung capacity, which is basically the largest lung volume. This is the maximum volume of the lung. Like this is the largest volume the lung can expand to, and it's equal to vital capacity plus residual volume, as I said. Once you take in the vital capacity, this big breath, then you're at TLC because you already have RV. RV is always inside lungs. It never changes, right? It never changes. So we have these 4, and now I'll explain it with a diagram that makes it so much easier. And this diagram, if you go look at practice questions, if you look at previous batch exams, it actually comes it's come in a few questions, and he doesn't mention it in the slide. So I would say pay attention here. First things first, what are we looking at? So this is a spirometer reading, and there's this bar graph, kinda. This is the maximal inspiration, which means if you're inspiring maximum, inspiratory reserve volume is over here. This is the resting expiration level, which means this is tidal volume when you're breathing outwards. And then this is maximal expiratory level, which is expiratory reserve volume, obviously, because you're trying to find out, you're trying to breathe out as much as you can, right? So this, ignore the graph. The graph doesn't really bother us right now. What we're bothered about is these blue lines. What are they? So the first thing is TLC. This whole thing is TLC because the TLC is everything in the lung volume, okay? Okay, actually, perhaps we should start from the residual volume. It's the easiest to understand. So residual volume is 0.5 liters. This is always present. It's never going to change. This is here, residual volume, this thing, okay? Now, usually you also have expiratory reserve volume unless you're forcing yourself to breathe this out. So this is expiratory reserve volume, and this is residual volume. And what do we have when we add expiratory reserve volume and residual volume? What do we have? Like, what's that thing called?
Residual capacity.
Yeah, we have the FRC, or the functional residual capacity. So this is just the addition of the residual volume and the expiratory reserve volume. This is what's usually left in the lung after you do a normal exhalation. Then we have vital capacity, which is the deepest breath that a person can take, right? So the breath is the vital capacity includes because the vital capacity, we're assuming that the person exhaled before this, like maximal exhalation. He has nothing in his lungs except this, which is residual volume. So he's adding all of this to his lungs. So the vital capacity is the expiratory reserve volume, the inspiratory volume, the tidal volume, and then the inspiratory reserve volume. So this entire breath is vital capacity. This thing where most of the breaths are, you see the graph, most of them are in this range. That's the tidal volume, which is completely normal, 0.5 liters. It's completely normal, and that's where most of the breaths are. Then we have inspiratory reserve volume, which is over here. This is excess inspiration, like excess exhalation. You're breathing in more than a normal person would. So you're adding this much air, inspiratory reserve volume. Okay, pretty self-explanatory. And then you have inspiratory capacity, which is inspiratory reserve volume plus tidal volume. So these two together form inspiratory capacity. We see it over here. Inspiratory capacity is inspiratory reserve volume plus tidal volume. So that's the spirometer reading. It could come in the exam, it could not, but it has come before. That's why I decided to mention it. So one more time, real quick. This is residual volume, which is over here, this much. This is always in the lung, never changes. We have tidal volume, which is 0.5, which is 0.5 liters. And this is what a normal inhalation exhalation pattern looks like. We have expiratory reserve volume, which a person exhales only if they're forced to. In a normal case, this would still be present, and that's what we call the functional residual capacity, which is a normal case when you're keeping both of these within the lung when you're exhaling. Then you have inspiratory reserve volume, which is the excess inspiration that you can take in, and you have inspiratory capacity, which is inspiratory reserve volume plus tidal volume. Then you have TLT, which is basically everything. Everything is TLC. And the formula for TLC is vital capacity plus residual volume. Okay. Now, very simple. We're done almost. Last part. Effective aging on the lungs. The lung volumes, all of them increase from 0 to 20. From 20 to 60, everything remains pretty normal in a physiological state, no changes. And 60 plus, residual volume keeps on increasing, but TLC remains the same. So when you reach 60 and you're more than 60, your residual volume, which is a volume in the lungs that can never be exhaled no matter how hard you try, it keeps on increasing. So in a normal person, we saw that was 1.5. So in an old person over 60, it might be 2. Okay. But the TLC, which is the total lung capacity, remains the same. So this thing is the same, and this thing is increasing. So what's that going to do to vital capacity? You remember this formula? TLC is vital capacity plus residual volume. We took it over here, right? Like just like a few minutes ago. So now let's say you're increasing the vital capacity, right? And your TLC is staying normal. So what's going to happen? Something has to give, and that's the residual volume. I'm sorry, you're not increasing the vital capacity. My bad, guys. You're increasing the residual volume, right? And the TLC is the same. The residual volume is increasing because of aging. So what's that going to do to the vital capacity? The vital capacity is going to decrease, which basically means that when you're old, your biggest breath is going to be smaller. Vital capacity is the biggest breath that you can take. It's expiratory reserve volume plus tidal volume plus inspiratory reserve volume. But this is going to decrease in old people because residual volume increases. Do you get that? Does everyone get that?
Yes.
Okay. So causes of reduced vital capacity, physiological cause is old age, which we just discussed over here. And then pathological could be due to weak respiratory muscles, lung disease, severe airway obstruction. Basically, anything that messes with the lungs is gonna decrease your vital capacity. Okay, and these are all pathological. The only physiological one is old age. I mentioned it over here. There is a graph for this in his lecture, which I forgot to add, but I can draw it for you. So this is the graph. It's like this. So the total lung volume, this is age over here, by the way. This is age, and this is lung volume here, volume. So the total lung volume or total lung capacity is gonna increase, and then you're 20. This is 20. You're 20 here. That's just 20, and then it's gonna stay the same until you're 60, and even after 60, it's the same because the total lung capacity doesn't increase after 20. Now you have the vital capacity, and the vital capacity also increases up till you're 20. Okay, maybe not that severely, but like, let's say the vital capacity also increases up to 20, which is this here. Okay. And then it's gonna, the vital capacity is gonna decrease after. Actually, it's gonna stay the same till you're 60 and then decrease. Obviously, this graph is not extremely accurate. It's very it has like a lot of, it's like exaggerated just so that I can explain it to you guys. But from 0 to 20, your lung volume, total lung capacity is increasing, and then it's going to stay normal. Your vital capacity is also increasing from 0 to 20, and then it's going to stay normal till you're 60, but then it's going to decrease. And the reason it's going to decrease is because the residual volume is going to increase. So the residual volume is this one, is going to plateau here, 20 to 60 is going to be normal, and then after 60 it's going to increase. So let me just, this is TLC. This is residual volume. And this is vital capacity. It's not actually this exaggerated. This is just to make you guys understand. The residual volume is normal until 60, and then it increases. Okay, we discussed this, and then we have our last slide. So just pay attention. By the way, guys, if a question were to come from this lecture, it's going to be this. Like, this is most probably what's going to happen. This is the question that's most likely to come. So just pay attention, and we're going to be done in 5 minutes. Obstructive versus restrictive lung disease. This is the most important thing in this lecture. Expect minimum 2 questions from this. So obstructive lung disease is when you have a high total lung capacity, very high residual volume, which also increases the functional residual capacity, because that's RV plus ERV. And then you have a high residual volume to total lung capacity ratio. Restrictive lung disease is low total lung capacity, low residual volume, which also means the FRC is low, because FRC is RV plus ERV, and normal RV over TLC ratio. Now, let's just break this down a bit. High TLC means in obstructive lung diseases, the total lung capacity is going to increase. Very high RV means in obstructive lung disease, residual volume is going to increase. And the high ratio. Why is the ratio high? The ratio is high because residual volume is very high, but TLC, or total lung capacity, is only high. So there's a difference in magnitude. It's not proportional. And because of that, there's a ratio. And the ratio would be high RV over TLC. When you divide this by this, it's going to be more than you would expect normally. Restrictive lung disease is the opposite. So you have low TLC, low RV, and normal RV over TLC ratio. Now, if TLC is low and RV is low, how is the ratio normal? And the ratio is normal because both of them are low. It's not like one is low and the other is very low. They're both low, and they're both decreasing proportionally. So there's a proportion. That's why the ratio stays the same. So obstructive and restrictive, right? If you have a doubt, by the way, please put it in the chat so I can clear it, because this is very important. Now, we've been saying obstructive, restrictive. What is obstructive and what is restrictive? Like, what's going on? Like, what's obstructive and restrictive? What's the difference? Like, what are these things? So obstructive lung diseases make it hard to exhale. Think of an obstruction. If you have an obstruction, you can't exhale. You have the air inside, but you can't exhale it. And this is why RV is high. RV, remember, is the volume which we cannot exhale no matter what. It's the volume that's always going to be present. And it's high here because you have a lung disease that makes it hard to exhale. So the air is going to be like, okay, I'll just stay here. You don't want me to go. And TLC is high because RV is high. You know, TLC, the total lung capacity, is affected by every single volume. So if RV is high, TLC is high. But as I mentioned here, the RV is very high and TLC is just high. That means the ratio is going to be elevated, more than normal. And this is a very important distinguishing characteristic between obstructive and restrictive. Obstructive, you have a high ratio, and restrictive, you have a normal ratio. Restrictive lung disease make it hard to inhale or breathe in. So obstructive make it hard to breathe out. Restrictive make it hard to breathe in. And the reason, I put it over here. You don't need to know the reason. It wasn't mentioned in the slides. I just thought that maybe if you know it, it would be maybe make it easier for you to know. You can read it in the slides, but I'm not going to explain it because it's not mentioned in the slides. Now, I have a question for you guys. What's alveolar ventilation? Can someone mention in the chat what's alveolar ventilation? or just speak it, no problem. This is the last thing, and then we're done. Pretty sure we're done. Yes, we're done. Just the last thing. What's alveolar ventilation? Can someone write it in the chat? It's the definition is right there, but like still. Okay, I guess no one wants to. What is alveolar ventilation? Is the volume of fresh gas entering the respiratory zone or the gas exchange zone per minute. And you guys remember that the respiratory zone or the gas exchange zone is basically the alveoli. So the volume of fresh gas entering the alveoli is alveolar ventilation. It's really that simple. And then there were 2 slides about the ideal gas law, and he said that they will not be tested in the exam. My bad. Tested in the exam. So I haven't included them, but you can still go over them for your own information. And we're done. Alhamdulillah. You can scan this code, and please scan it. It's just one question. It's going to take like 10 seconds to fill out. And we're done. I'm here if anyone has any questions to ask. And yeah, that's it. We're done. Alhamdulillah. If you have a question, if you want me to explain something, I'm here. No, thank you for attending, wallah. I guess that's it then. We can stop recording. I am in.